Okie dokie. So we're reaching the end here of the aromatics chapter, and just had a couple of reactions that I wanted to go over. I wanted to talk to you guys about one kind of oddball reaction, and then I wanted to move into the idea of what we'll call coupling reactions. And I might split this up into a couple different videos, probably split up into two different videos. But anyway, let's talk about the oddball reaction here. So, if we start out with Mr. Alkene, and I ask you, how can I turn Mr. Alkene into a vicinal dihalide, a vicinal diol. Wow, words failing me. Let's try this one more time. Vicinal diol. There it is. Okay. Spelling is good. Then, there's a couple of reactions that we learned that how you could do that. We could do it in one step. We could do it in a couple different steps. Depending on the stereochemistry that we wanted, right? It'd be important to kind of pay attention to that, but it doesn't really matter in this case here, at least. So how could we do that? Well, one of the options that we have was to take potassium permanganate. Wow. Some days. Potassium permanganate, and we put in some water and some sodium hydroxide, and, excuse me, and we try and keep this cold, and that would accomplish that reaction, okay? If we take the exact same compound and we do this, right, and then heat it up, right, then we break the carbon-carbon bond, right? We would break the carbon-carbon bond and end up forming the carboxylic acid, of course, after we do an acid workup and all that other kind of stuff, right? But just we're kind of, I'm just making a point here, right? And so our potassium permanganate is a very good oxidizing agent, and it'll oxidize pretty much everything. Now, if you recall, when we first introduced this idea of oxidation and all this, we made the point about selectivity. And potassium permanganate really is not selective, okay? And in fact, we can use it to do some fairly useful chemistry, well, useful at times. So let's say that we have our buddy toluene here. And if we take toluene and we put it under these harshly oxidizing conditions, we will get a reaction where we will actually oxidize that carbon and turn it into a carboxylic acid. So, wow, that's pretty weird, right? Because if we just take, let's say we just take butane, right, and we put it under the same conditions, nothing's going to happen, right? Nothing significant is going to happen. So the point is that our carbon here, our benzylic carbon, is a very reactive position, right? It's easier to stabilize a carbocation there, right? We can generate radicals there pretty easily. We can do a lot of useful chemistry by having that benzylic carbon there. Say, okay, what are the limitations? What are the scopes of this? So if we take our buddy aromatic ring, we got our buddy toluene. Let's say we make a derivative of styrene here, right? So we got that vinyl benzene there. Same thing. Here's our product. I'll draw it like this. So we end up taking both of our positions there and just chewing them off. Say, geez, okay. Well, can we ever slow down this beast? Well, the answer is yes. If we try and do this, Then we can finally satiate the beast, and that will be our product. Okay? The point being this, right? Whoops. Let's do it like this. What is different between the red and the green carbon in our starting material? What is different about the red and the green carbon in our starting material? What is different about any of the green carbons as opposed to the red carbon? And the difference is, does it have a CH bond? Okay, so to get this reaction to go, we're going to need to have a benzylic hydrogen. Okay, we're going to need to have at least a hydrogen, right, on that benzylic carbon. Okay, but if we have a T-butyl group or a tertiary carbon there, or a quaternary carbon, I really should say, if we have a quaternary carbon there, doesn't have a CH on it, it's not going to be that susceptible to this oxidation. All right. So we can use potassium permanganate to basically chew off an alkyl group and leave a carboxylic acid in its place. And you're like, well, why in the world would we care about this, or what's the point? Well, you know, it is another way of introducing, right? It is another way of introducing a carboxylic acid. So think about it here for just a second. Well, let me pick a different color to make this stand out. Yellow seems good. Okay. So think about this reaction here for a second. Okay, what are we doing? So in the starting material, right, we've got an alkyl group on there, and alkyl groups are electron donating, right, and they can make things go ortho or para. But in our product, right, we've got a carboxylic acid, which is an electron withdrawing and a meta director. Okay, so we can use this, if we want to think about it for a second, right? We can use this as a way to change an alkyl group from an electron donating into an electron withdrawing group. So by changing it into a carboxylic acid, okay? So there's a potential application. This is actually a reaction we sometimes do in the lab. And the reason why is because when this reaction is done, it precipitates out this fine brown powder, which is manganese 4 oxide. And so it's got a visual indicator about whether this reaction is happening or not. And, you know, that helps us to detect certain functional groups, right? It can be used to detect, double bonds and benzylic carbons and all this kind of stuff, right? So this is also a qualitative analysis reaction, right? If we have an unknown compound and we put some of this permanganate in there and let it go, if it starts to oxidize something, we can see that its oxidation is happening by the precipitation of the manganese dioxide that happens at the end there. Okay, let's see, how are we doing on time here? You know what? Okay, so here's what we'll do. I'm sorry I lied at the beginning. We'll just end this one video here. It'll be nice and short, and then we can chunk together all the other coupling reactions into one, and that'll kind of make a nice little story to tell there. Okay, so there are a couple other reactions that they talk about in the book, just to wrap things up here, right? They do talk about addition reactions, where if you've got benzene and you put it under high pressure, right? High pressure and temperature with chlorine, you can make the hexachloro derivative, right? But we're talking about like thousands of psi, right? Thousands of atmospheres. Like, it's just, yeah, we can break an aromatic ring, but you're going to need a lot to do this, right? And plus, what practicality does hexachlorocyclohexane really have? Like, I really don't know, but maybe there's something for it. But anyway, so there are a couple other reactions in the book, and read through it, look at it. That'd be useful for you to have. But I just kind of wanted to introduce the permanganate reaction here to remind ourselves about selectivity, and then to talk about how we can use, right, its oxidative capacity to kind of work with the alkyl groups and change it from a donating group into a withdrawing group. Okay. All right. That's it for this video. I'll see you guys on the next video for coupling reactions.